Hello, my dear students. Welcome to the session. Continuation of important observations from our electronic concept. Now I'm going to starting module 2 rectifiers into this. In this session, with respect to rectifiers, I would like to discuss about single phase diode rectifier is and control. First, we have to start with some introduction to power electronic converter. Students, we know that power electronic circuits are broadly classified into different types. One is AC to DC. In AC to DC converters, input AC, that is at output side we can get the control voltage or variable voltage or pulsating DC. The converter which converts AC to DC with variable voltage, those converters are called rectifier. That is, rectifier is a converter which converts AC to DC with variable voltage at output side. One more converter is DC to AC converter. In DC to AC converters, input DC, output AC. At output side, we have to control the voltage. We can control the frequency. We can also control the number of phases. What do you mean by controlling the number of phases at output side? We can convert DC to single phase AC. We can convert DC to three phase AC. That is the meaning of controlling the number of phases at the output side. That is, in inverter, voltage is controlled, frequency is controlled, number of phases also controlled. The converter which converts DC to AC, the converter which transfers power from DC to AC, those converters are called inverter. Rectifier is a converter. Even inverter is also converter. Point to remember, friends. Every power electronic circuit is a converter because converter is the general term is used for all the power electronic circuits. Rectifier is a converter. Inverter is also converter. Stopper is also converter. AC voltage controller also converter. Cyclo converter is also converter. That is, every power electronic circuit is a converter. But rectifier is not an inverter, inverter is not a rectifier. But every power electronic circuit is a converter because converter is the general term. That point you have to remember. One more converter is DC to DC converter. In DC to DC converters, input DC, output is also DC. But at output side, voltage is stable or controlled voltage. The converters which converts DC to DC. The converters which converts DC to DC are the converters which transfers power from DC to DC. Those converters are called super, or it is also called SMPS. It's also important. Switched mode power supplies. SMPS also DC to DC converters. Super also DC to DC converters. What is the main difference here? DC to DC converter with high power application is called chopper. DC to DC converter with low power application is called SMPS. For example, chopper fed DC motor because it's a high power. SMPS fed CPU because it's a low power. Both are DC to DC converter. High power application it is called chopper. Low power application it is called. One more converter. Input AC. Output is also AC with variable voltage. That is, voltage is variable, frequency constant. Important. Frequency constant in the sense input frequency is F. If input frequency F, then output frequency is also F. There is no change in frequency. Output frequency is also F. Only which is variable here? Voltage is variable. Those converters are called AC voltage controllers, or it is also called AC voltage regulators. The converters which converts AC to AC with variable voltage constant frequency. Important. Voltage is variable, frequency constant. Those converters are called AC voltage controller. One more AC to AC converter. This is also AC to AC converter. Also AC to AC converter. That is, input is AC. Input is AC. Output is also AC. But at output side, voltage is variable. How to vary the voltage? Frequency is also variable. Voltage is controllable. Frequency is also controllable. Frequency controllable in the sense, for example, let input frequency is F in, output frequency is F naught. We can make either F in greater than F naught or F naught greater than F in. We can step up the frequency or step down the frequency. Is F naught less than F in or F naught greater than? Those converters are called cyclo converter. That is the converter which converts AC to AC with variable voltage and variable frequency. Those converters are called cyclo converter. Or sometimes it is also called matrix converter. This statement I already given. Please go through this. Converter is a general term referred for all power electronics. Every power electronic circuit is a converter. Rectifier is a converter. Inverter is also converter. Stopper is also converter. AC voltage controller is also converter. Cyclo converter is also. These are the different power electronic circuits that are developed based on the application. For going to starting diode rectifier, single phase diode rectifiers, that is uncontrolled rectifiers. First, we have to see some fundamental points. Friends, we know that these are the AC waveforms. I'm talking about pure AC. Pure AC in the sense, for any waveform, the average value is 0. That waveforms are treated as a AC waveform. But in AC, there is a sinusoidal, again non-sinusoidal waveforms are present. This is the sinusoidal AC component. It consists of only fundamental. There is no harmonic. It is a non-sinusoidal waveform. It consists of fundamental and harmonics. That it is a symmetrical AC waveform. If it is a symmetrical AC waveform, then it consists of only odd harmonics. All the even harmonics are zero. Now from this we have to define what is the total harmonic distortion. This formula you have to remember. Total harmonic distortion equal to RMS value of harmonic by RMS value of fundamental. What is the RMS value of harmonic? This is also important formula. Very important observation that you have to consider. RMS value of harmonic equal to total RMS square minus fundamental RMS. That is, from the total RMS, if you subtract the fundamental value, remaining is the harmonic value. Understand? From total RMS, if you subtract the fundamental RMS, what is the remaining term? Remaining is the RMS value of harmonic. That RMS value of harmonic by RMS value of fundamental is called total harmonic distortion. This one formula you have to remember. RMS value of harmonic you remember, total harmonic distortion also you remember. These terms I given, please go through this. XR is the total RMS, X1 is the RMS value of fundamental, XH is the RMS value of harmonic. This one more way to write this formula, RMS value of harmonic by fundamental RMS. This is called total harmonic. By simplifying this, we can also write the formula like this. Total harmonic distortion equal to XR by X1 whole square minus 1 whole to the power of 1 by, where XR by X1 is 1 by DF. This one more important formula. This is called distortion factor. Distortion factor equal to fundamental RMS by total RMS. Very important. This is the distortion factor with respect to fundamental. Fundamental RMS by total RMS. Then X1 by XR. But here XR by X1, that's why 1 by DF. This is one more important formula. Total harmonic distortion in terms of distortion factor. But point you have to remember here, friends. If distortion factor equal to 1, total harmonic distortion is 0. Total harmonic distortion is 0 means there is no any harmonics. That is pure sinusoid. That is what is the observation here. If distortion factor is decreases, if distortion factor is decreases, this is decreases, total harmonic distortion is increases. Total harmonic distortion is increases means the quality of AC waveform is decreases. What do you mean by reducing the quality of AC waveform? Uh, a waveform is whose nature is away from the sinusoidal nature. That is the meaning of quality is reducing. That's why if any waveform is having the high value of total harmonic distortion, that nature is deviated from the sine wave. Deviated from the sine wave. Hence, the quality of AC waveform is measured by two factors. The quality of AC waveform is measured by two factors. Which factors? One is total harmonic distortion, another one is a distortion factor. Point to remember, students, if distortion factor is increases, total harmonic distortion is reduced. If any waveform is having high distortion factor, the total harmonic distortion is less. If the total harmonic distortion is less, the quality of AC waveform is more. What do you mean by quality of AC waveform is more? Whose nature is nearer to sine wave. Next, we'll see the one more basic here, DC waveform. AC waveform, which parameters we have to use to analyze the quality? Distortion factor and total harmonic distortion. Similarly, for DC waveform, to analyze the quality, we are using two factors. One is ripple factor, another one is form factor. How to get the ripple factors? Ripple factor equal to, this is the formula for the ripple factor. RMS value of AC by average value. This is the fundamental formula. RMS value of AC by average value. This is the ripple factors. Ripple factor equal to RMS value of AC. How to get RMS value of AC? From total RMS, you subtract average value. Total RMS, you subtract average. Average means DC. From total RMS, you subtract DC, we can get only AC. That is called XAC, student. That is RMS value of AC by average value. By simplifying this XR by XDC. RMS value by average value. What this RMS value by average value is called form factor. This is the relation between ripple factor and form factor. Also you have to. That is ripple factor equal to square root form factor square minus. Then form factor equal to RMS value by average. The quality of DC is measured by form factor and ripple factor. If form factor equal to 1, the ripple factor 0. Ripple factor is 0 means there is no ripples. There is no ripples means DC does not consist of AC term. In DC, if there is any AC is present, that is called ripples. What I am telling here, if the form factor is 1, what is the ripple factor? 0. The ripple factor is 0 means pure DC. That is for pure DC, what is the form factor? Important. For pure DC, form factor equal to 1. For pure DC, important students. For pure DC, what is the form factor? Form factor equal. If the form factor equal to 1, ripple factor is 0. That is, if the form factor is increases, ripple factor is increases, quality of DC is decreases. Exactly opposite. If form factor is decreases, ripple factor is decreases. If ripple factor is decreases, but the quality of DC increases. High quality in the sense, the nature is nearer to pure DC. There is nearer to pure DC. There is no any ripple content. Some basic points with respect to AC waveform and DC waveforms. This one problem that you have to practice. One question. For a non-sinusoidal output, V3 by V1 is X, V5 by V1 is Y. Find the total harmonic distortion. What the total harmonic distortion? RMS value of harmonic by RMS value of fundamental. What is the RMS value of harmonic? Which harmonics they given? Third harmonic and fifth harmonic. V3 square plus V5 square by V1. Then you bring this V1 into the square root. V3 by V1 whole square, V5 by V1 whole square. What is the V3 by V1? They X, V5 by Y. Substitute. Total harmonic distortion equal to root of X square. This we have to practice. Before starting the rectifiers concept, very fundamental, one more fundamental concept. Performance parameters of rectifier. Throughout study of rectifiers or power electronic circuits, we have to know these performance parameters and fundamental formulas. These are the fundamental formulas. Based on these fundamental formulas, already questions are there in GATE exam. 2 marks questions also framed mainly in input performance parameters, not in output performance parameters. Input performance parameter, 2 marks questions are framed. When output performance parameters also questions are repeated, sir. Don't neglect. There is one formula is there, ripple frequency. Already questions are there in GATE. With respect to input performance parameters, input power factor, displacement factor, those two formulas, repeated questions in the GATE exam. Yes. These are the some input performance. First, I am going to explain in output performance parameters. In output performance parameters, one parameter is average output voltage. This average value is also called mean voltage. And these formulas, these are the fundamental formulas. Please go through this one. And this is the RMS value. Don't want to explain derivation, all this. This is the minimum fundamental formulas. Please go through this. There's a quick revision that you have to concentrate. Form factor, that is RMS value by average value. Ripple factor, RMS value of AC by average value. That is ripple factor equal to square root form factor square minus 1. DC power equal to average voltage into average current. AC power equal to RMS voltage into RMS current. Rectification efficiency equal to output DC power by output AC power. Important, sir. Output DC, both are defined at output side, not at input side. Not at input side. Both are defined at output side. Important. Output DC power is V naught into I naught. Output AC power is V naught RMS into I naught. You have the doubt, yes, sir. Efficiency is output by input, sir. But in rectifiers, input is pure AC. Output is DC. We don't compare with the DC with the. We are comparing at output side only. That's why output DC power by output AC. If you want percentage efficiency, multiply into 100. Transformer utilization factor, output DC power by input secondary volt amperes. Every formula important. Output DC power by input secondary volt amperes. Ripple frequency. This is 5-star gunshot. This is very important. Even this formula is also important. Even rectification efficiency formula is also important. Formulas are important. How to define ripple frequency? Number of cycles per cycle into number of pulses, not cycles, number of pulses per cycle. Per cycle, how many pulses are there into frequency? That gives the ripple frequency. Number of pulses per cycle. If there is one pulse per cycle, that is called one pulse converter. If there is a 3 pulses per cycle, 3 pulse converter. 2 pulses per cycle, 2 pulse converter. If it is a p pulses per cycle, then it is a p pulse. For example, if they are given 3 pulse converter, what is the meaning of 3 pulse? 3 pulses per cycle. That is in that rectifier, 3 pulses per cycle. That is the meaning. If they are given 6 pulse converter, what is the meaning of 6 pulse converter? That is 6 pulses per cycle. 6 pulses per cycle. That is the meaning. That pulse number directly indicates the pulse converter. P pulse means P pulses per cycle. This important observation. For single phase half wave rectifier, it is 1 pulse converter. Ripple frequency is 1 into F, that is F. How many pulse converter? The 1 pulse converter. Single phase half wave rectifier is a 1 pulse converter. Single phase full wave rectifier is a 2 pulse converter. Ripple frequency is 2F. Single phase semi converter also 2 pulse converter. Ripple frequency is 2F. Half wave rectifier. Full wave rectifier or fully controlled rectifier. Full wave, single phase, full wave or fully controlled rectifier. Full wave or fully controlled. Different names. Even diode rectifiers it is applicable. Thyristor rectifiers also it is applicable. Fully controlled rectifier. Single phase semi converter it is also called half controlled rectifier. Semi converter is also called of controlled rectifier. Of control. Single phase full wave rectifier is a 2 pulse converter. Semi converter also. Single phase half wave rectifier is 1 pulse converter. 3 phase half wave rectifier is 3 pulse converter. That is 3 into F, ripple frequency 3F. 3 phase full wave rectifier is how many pulse converter? 6 pulse converter. Ripple frequency 6 into F, 6F. Important. The next circuit is very important. 3 phase semi converter. But 3 phase semi converter is, it's both 3 pulse and 6 pulse converter. This is important observation. 3 phase semi converter is 3 pulses are exist, 6 pulses also exist. For firing angle less than 60 degrees, it is a 6 pulse converter whose ripple frequency is 6. For firing angle greater than 60 degrees, it is a 3 pulse converter ripple frequency. That's why which converter is both 3 pulse and 6 pulse converter? Question is asked like this. Which converter is both 3 pulse and 6 pulse converter? That is semi converter is both 3 phase semi converter, not single phase. 3 phase semi converter is both 3 pulse and 6 pulse semi. When it is a 6 pulse converter, firing angle is less than 60. When it is a 3 pulse semi converter, if the firing angle is greater than or equal to 60, firing angle is greater than or equal to 60 degree. It is a 3 pulse converter. That is only for this 3 phase semi converter only. Based on the firing angle range, the number of pulses will change, then ripple frequency also will change. But remaining converters, it is independent of firing angle. Then here I am giving the generalized statement. For 1 pulse converter, ripple frequency F, 2 pulse 2F, 12 pulse 12F, P pulse PF. For example, for 12 pulse converter, what is the ripple frequency? The question is asked. 12F only. 6 pulse converter, what is the ripple frequency? 6F only. 3 pulse converter, what is the ripple? 3F. Like this we have to. Based on this, one model of question that you have to consider. A single phase controlled single phase full bridge converter is supplying highly inductive DC load. Given that single phase full bridge converter. Single phase full bridge converter is single phase full wave rectifier. Single phase full wave rectifier, what is the ripple frequency? 2F. Frequency 50 Hz, 2 into F, 100 Hz. The answer is ripple frequency at the output side or DC side. DC side in the sense output side. What is the ripple frequency? Like this. For example, if the question is asked, a 3-phase fully controlled rectifier. 3-phase fully controlled rectifier operating with a supply voltage 400 volts 50 Hz. What is the ripple frequency? 3-phase fully controlled rectifier. 3-phase fully controlled rectifier is 6 pulse converter. 6 into 50, 300 Hz. Like that you have to answer. Understand? How many number of pulses per cycle? That into frequency. That gives the ripple frequency. What is the input performance parameter? The input performance parameters of rectifiers. There is so many input performance parameters. Before this point you have to remember. Source current waveform is also very important. Most of the competitive exam, the questions are asking, what is the nature of the source current waveform? For single phase half wave rectifiers, important. Generalized statements, easy to remember. For single phase half wave rectifier, it may be diode rectifier or thyristor rectifier. Both the cases it is applicable. Thyristor rectifier in the sense phase control rectifiers. For single phase half wave rectifier, for any load, R load, RL load, RE load, RLE load, RL and freewheeling diode, RLE and freewheeling diode, for any load, input or source current waveform or supply current waveform, pulse weighting DC. That is fixed. Half wave rectifier, any load, pulse weighting DC, sir. I am not talking about pure inductor, pure capacitor. Practical cases I am telling. Single phase full wave rectifier. R load and RE load, input or source current is sinusoidal. Single phase full wave rectifier, R load and RE load, input source current is sinusoidal. If they given RL load and RLE load, let assume that it is a continuous mode. Source current is a square wave. Unless otherwise specified, full wave rectifier RL and RLE load is the continuous mode only. That's why source current is square wave. RL with freewheeling diode or RLE with freewheeling diode. Source current is the quasi square wave. Current is quasi. That is, in full wave rectifier, three waveforms are exist. Source current waveform. Source current waveform means that is a secondary current. Source in the sense secondary current. I'm not talking about primary. Primary is always sinusoidal. Talking about secondary. The nature of the secondary current wave. Source current in the sense you have to take the secondary current waveform. That is, in full wave rectifier, there exists three types of waveforms. R load, RE load, one waveform. RL load, RLE load, one waveform. RL and freewheeling diode, RLE and freewheeling diode, quasi square. What about single phase semi converter? In single phase semi converter, R load and RE load sinusoidal. Remaining loads quasi wave. That in semi converter, two waveforms are exist. Without inductor case, sinusoidal. With inductor case, is a quasi square wave. With inductor case, it is a quasi. Half wave rectifier, any load, only pulse waiting DC. Full wave rectifier, single phase. I'm talking about only single phase this. R load, RE load, sinusoidal. RL, RLE, square wave. With freewheeling diode, quasi wave. In single phase semi converter, R and RE loads, sinusoidal. Remaining loads, RL load, RLE load, with freewheeling diode. All these cases only one waveform, that is quasi wave. Now with this knowledge, let's assume that this is the source voltage or secondary voltage waveform. This is the secondary current waveform. Secondary current never be sinusoidal because it consists of harmonics. And this is the fundamental secondary current. IS1 is the fundamental secondary current. The angle between secondary voltage and fundamental secondary current is called displacement angle. The angle between Vs and IS1 is displacement angle. Let capital Vs equal to RMS value of source voltage or RMS value of secondary voltage. Is equal to RMS value of source current or secondary. Here source in the sense secondary only with respect to transformer. IS1 equal to RMS value of fundamental secondary. With this knowledge, what the displacement angle? Angle between secondary voltage, fundamental secondary current is displacement angle. Cause of displacement angle is called displacement factor. What the active power input or active power drawn by the converters? That is, how much active power drawn by the converter? How much active power we are applying to the converter? How much active power we are applying to the converter? That is Vs into IS1 into cos phi 1. IS1 is RMS value of fundamental source current, not the total RMS source current, only RMS value of fundamental source current. For the reactive power drawn by the converter, Vs into IS1 into sin phi 1. For the current distortion factor, IS1 by S. For the total harmonic distortion that I told already, 1 by distortion factor square minus 1 whole to the power of 1 by 2 r RMS square minus fundamental RMS square by fundamental RMS square whole to the power of 1 by 2. All these observations are important. Very, very important 5-star formulas. Input performance parameters are very important. Every formula is important. So many times based on this question is there. Even displacement factor, so many times the questions are that you have to consider. Different computations. That is input power factor equal to active power delivered to the load by input secondary volt ampere or average power by, here active power is nothing but which power, students? Active power is nothing but average power by input secondary volt ampere. That is average power by, here input secondary volt amperes means VA rating of transformer. Important. Input secondary volt amperes are nothing but a VA rating of transformer. This is single phase transformer. Then one of the fundamental formula for input power factor equal to IS1 by IS into cos phi. We can also write input power factor in terms of current distortion factor and displacement factor. Current distortion factor in displacement. Then we have to define crest factor. Is peak value by RMS value. This crest factor is also called peak factor. Peak value by RMS. These are the input performance parameters. In different cases, this is V of t, this is I of t, does not having the harmonics. How to find active power, reactive power, apparent power, power factor. Concentrate. Note 2. If Voltage is having harmonics. Current is also having harmonics. Then how to find the active power, reactive power, RMS voltage, RMS current, apparent power, power factors. That you have to concentrate. This is power factor equal to P by S. P is active power, S is apparent. This is important in power electronics. Power electronics point of view, this is important. Note 3 is important. This is used in power electronics. Voltage does not having harmonics, only current is having harmonics. Both voltage and current is having harmonics, apply like this. But here only current is having harmonics, voltage does not having harmonics. Then how to calculate active power, reactive power? Vrms is Vm1 by root 2. This is Irms. Then apparent power, then power factor, apparent power and power factor. That you have to. The input voltage is given to the converter. This model is repeated in gate exam. Repeated. This input voltage is given, input current it is given, displacement angle, displacement factors. First we have to find displacement angle. Displacement angle means this is fundamental voltage. Fundamental, there is no harmonics. This first we identify the fundamental current. Which is the fundamental current? This frequency and this frequency is equal. Then it is a fundamental current. Then what is the angle between these two? Only this current is the fundamental. Only this current is the fundamental. Angle between Vs and Is1 is pi by 3. Displacement angle. Once you know the displacement angle, how to find displacement factor? Cos of displacement angle is 0.2. Next, you have to find the input power factor of the converter. What is the input power factor of the converter? Is1 by Is into cos pi 1. This is the Vs, RMS value of secondary voltage. This is the peak value. Peak value by root 2, that is RMS value. I am finding the total RMS value of secondary current. How to find the total RMS value of secondary current? This by this root 2 whole square. This by this root 2 whole square. This by this root 2 whole square. This is the total secondary current. But I have to find only RMS value of fundamental source current. Which is the fundamental? Because this frequency and this frequency is equal now. That's why this only the fundamental. But these are 3 times. These are 5 times. Third harmonic. This is third harmonic current. This fifth harmonic current. Then this is the only fundamental current. What is the RMS value of fundamental current? Peak value by root 2. This is 10. Then apply all the formulas. Input power factor formula you know. Active power input formula you know. Reactive power input formula you know. TDF, current distortion factor formula you know. THD formula you know. Please practice these questions. After practicing all these formulas, you have to practice this question because this model is repeated in gate exam. Then this is the question based on the input power factor definition. Input power factor. And this question also you have to practice. Both are having harmonics. How to find active power? Already given. You find the Vrms, Irms separately. Then you can get the S. Then P by S gives the input power. See this problem and this problem. This problem only current is harmonics. But what about here? Voltage is having harmonics. Current is also having harmonics. How to answer? This models is important even in your measurement subject point of view, even signals and systems point of view, even AC analysis of network theory point of view also it is important. With this knowledge, now I am going to starting single phase diode rectifiers, that is uncontrolled. The first circuit, single phase half wave diode rectifier. Half wave is only one diode. Single phase half wave diode rectifier using R load. No need to explain in detail about the operation. Positive half cycle diode will conduct. Negative half cycle diode is reverse bias. But point to remember, sometimes they will give the supply directly like this. Sometimes they will give the through transformer. If they given the true transformer, this primary voltage directly don't take in calculation. You calculate the secondary voltage using turns ratio. If the turns ratio they given, according to turns ratio, calculate the secondary voltage. If the supply is given like this, then how to find the RMS value? Vm by root. Single phase 230 volts 50 Hz it is given. This directly gives RMS value. Without function, that is the RMS value. With the function they given, this is the maximum value. How to find RMS value? By root we have to do. Then these are the very important observation. Single phase diode rectifier single phase half wave diode rectifier using R load. This is for single phase half wave diode rectifier. Half wave. Every formula is important. Half wave diode rectifier using R load. Rectifier R load. With respect to resistive load, for half wave diode rectifier, what is the peak inverse voltage? Where the current is maximum? Current is maximum at 90 degrees and current is 0 at 80 degrees. Then diode conduction angle is how much? 180 degrees. What is the circuit turn off time? Pi by omega. This is important. Half wave, all these applicable for diode rectifier for R load. Single phase half wave diode rectifier R load. What is the average output voltage? Vm by pi. RMS output voltage also you have to calculate. That RMS output voltage Vm by 2 and this is the RMS output. But instead of doing all this integration, this is the generalized formula. Just substitute lower limit and upper limit. Cos of lower limit minus cos of upper limit. And time period you have to substitute. This we can get the average value. This is the RMS value. To calculate average and RMS values very easily, you have to use these generalized formulas. By using these generalized formulas, you can easily calculate the average and RMS values. Yeah, this please go through this. All these formulas are with respect to resistive load. Single phase half wave diode rectifier. But the output power V naught RMS square by R. If it is a output power, you have to resistive load, use the RMS values. Don't use the average value. It is output power with respect to resistive load, use the RMS value. Input power factor, because it is a discontinuous mode. In discontinuous mode of operation, you have to use RMS value. This V naught RMS into I naught RMS by Vs into Is. In single phase half wave diode rectifier with resistive load, this is the input power factor formula. This is a DC power, AC power, form factor, ripple factor. All this one time you have to practice. This is about single phase half wave diode rectifier with resistive load. Sometimes by giving the question combination of measurements and power electron. This is PMMC ammeter, MI ammeter, PMMC voltmeter, MI voltmeter. If the question is asked what is the reading of this one, or the PMMC meter measures average value. Average current is Im by pi. But what is Im here? Vm by R square. What the Mi measures RMS current? That is Im by 2. But the PMMC voltmeter measures average voltage, Em by pi. Mi voltmeter measures RMS voltage, Em by 2. That formulas I already given. And this waveforms, you have to go through this waveform, but no need to practice this. Don't expect any waveform based on the circuit. But one observation here, how many pulses per cycle? This is in half wave rectifier. Any half wave rectifier, any load, how many pulses per cycle? One pulse per cycle. Only one pulse per cycle. This one pulse per cycle, that's why it is a one pulse converter, or it is also called single pulse converter. Pulse converter, or it is also called pulse converter. Then what is the ripple frequency? If it is one pulse converter or single pulse converter, what is the ripple frequency? 1 f, whole f, circuit turn off time. That this is with respect to resistive. And you practice this question. One point you have to concentrate here, students. You don't have any time to practice all the formulas. Whatever the model of problem that I given, please go through this model of problem. Try to practice minimum the question, whatever the question. Maximum from that model only you can expect. From that model only you can expect. This is the question I solved with respect to single phase half wave diode rectifier or single phase single pulse converter. Half wave diode rectifier is single phase half wave diode rectifier is one pulse converter. All this problem you have to practice. Next, purely inductive load. Purely inductive load concept is very important in single phase half wave. In single phase half wave diode rectifier with respect to purely inductive load, these are the observations. What is the instantaneous output current expression? Go through this one. Vm by omega L into 1 minus cos omega t. No need to make any derivation here. This formula you have to concentrate. And these observations are important. And no need to concentrate on the waveforms. This is the current waveform, this is the voltage waveform. That is for purely inductive load, input waveform and output waveform is same. This is the only ideal case. Practically, this type of loads are not exist. For purely inductive load, input waveform and output waveform is voltage waveform, not the current waveform. Input voltage waveform and output voltage waveforms are. And this observe analysis only important. Every rectifier, no need to practice the waveforms. Mainly analysis formulas, whatever I given, that formulas you have to concentrate. You don't have the time to practice these formulas. Whatever the model of question that I solved, minimum you have to practice that model, friends. Then peak inverse voltage 0, circuit turn off time 0. This is the instantaneous output current. Where the current is maximum pi, where the current is 0 to. Diode conduction angle. This is important. Purely inductive load, how much angle the diode will conduct? 360 degrees. Then what the peak load current expression? I max equal to Vm by omega L. What the average load current? For purely inductive load, the average load current is M by. Then what is the average output current? The same formula that I given. This is RMS output. There is a different way of calculations also I given. Final formulas only how to come. Sorry. This is RMS output current. RMS output current equal to root 3 by 2 into this Vm by omega. What is Vm by omega? I naught equal to Vm by omega. This is I naught equal to Vm by omega. So I am replacing with I naught with the Vm by omega. I naught. So this mainly how to concentrate with respect to. Then what is the ratio of I max, I naught, I naught? This is also important. But the average output, this is important. For purely inductive load, average output voltage is. What is the RMS output voltage? That is Vm by root 2. The output waveform is sinusoidal. Current waveform is rectified, but voltage waveform is not rectified. That you see. Then this is the question by combination of measurements and power. Here PMMC ammeter, my ammeter, PMMC voltmeter, my voltmeter. PMMC ammeter measures average current. Average current is Vm by omega. What the MI ammeter measures RMS current, root 3 by 2 Vm by omega. What the PMMC voltmeter measures average value. What is the average voltage with respect to pure inductor? 0. This is RMS output voltage. That you have to. And that I solved one model of question. Please practice this question. If you are not practicing the whatever the formulas that I given, it's better to practice this model of question. One more configuration of single phase half wave diode rectifier, that is using RL load. This is the configuration using RL load. And with respect to RL load also, before starting the RL load conduction angles, all this point to remember, students. For R load, current is maximum at pi by 2, current is 0 at pi. L load, current is maximum at pi, current is 0 at 2 pi. Important observation. RL load in between pi by 2 and pi. Thus, R load pi by 2, L load pi means RL load in between pi by 2 and pi. Where the current is 0 between pi and 2 pi, that angle is taken as a beta, where beta is called extinction angle. The beta is called extinction angle. That is, for large inductor, beta is nearer to pi. For small inductor, pi is 2 pi. Beta is nearer to 2 pi if it is a large inductor. For small inductor, beta is nearer to pi. For the beta here, beta is the that you have to concept. Then this is the peak inverse voltage. This is the circuit turn off time. This is a diode conduction angle. Average output voltage. This is for RL load. Single phase half wave diode rectifier. Single phase half wave diode rectifier using RL loads. And this is the RMS output voltage. This is the RMS source current, and this is output power expression. Because in discontinuous mode, you have to use V naught RMS square by R. This is the input power factor, and input power factor equal to V naught RMS by. And this is the waveforms with respect to RL. You need to practice these waveforms, leave it. Mainly circuit turn off time is important. 2 pi minus beta by. And this one more observation, you have to concentrate with respect to RL load. This is 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 the sinusoidal component, IT is the exponent. That means in RL load, the output current consists of sinusoidal component of current and transient component of current. Which is the transient component of current here? The exponential current is the transient component of current. This is the sinusoidal component of current. Then this observation is also important. For R load, how much angle current is supplied to the load? 180 degrees. This is the average output. L load, 360 degrees current is supplied to the load. Average output voltage. RL load, only beta angle current is supplied to the load, but average output voltage. That is, in which load the average output voltage is more? Resistive load. Which load the current supplied to the load is less? That is resistive. That is what is the observation here, students. Higher the inductance, the conduction angles, more time you can supply the current to the load, but average output voltage is less. That is, if the load inductance is increases, important observation. The load inductance is increases, conduction angles are increases, but average voltage is reduced. Load inductance is increases, conduction angle. That means more time, more angle we can supply the current to the load, but average output voltage is. If the average output voltage is reduces, power output reduces, efficiency will reduces, input power factor reduces. This is the problem. Now the question is, without reducing average output voltage, we have to supply continuous current to the load. For that, we are connecting the freewheeling diode or flywheel diode or commutating diode. For this reason, we are using the with freewheeling diode. This is the circuit with freewheeling diode that you have to concentrate on the. These are the waveforms. Let us assume that is a continuous mode of operation. We are supplying the constant current. Simply remember, students, in half wave rectifier, only one case only continuous mode is exists. That is with freewheeling diode case. Remaining cases discontinuous mode. That means we can't supply continuous current to the load in one cycle, except freewheeling diode case. In freewheeling diode case only, in half wave, I am talking about half wave rectifier. In half wave rectifier, which configuration continuous mode is possible? It may be diode rectifier or it may be thyristor rectifier. Only freewheeling diode case only continuous mode is possible. Remaining cases discontinuous. Continuous mode means let us assume that we are supplying the constant current. Then this is the discontinuous mode, but unless otherwise specified, you have to take the continuous mode. This mainly our analysis is continuous mode only. Peak inverse voltage, circuit turn off time, how much main diode conduction angle, freewheeling diode conduction angle, average output voltage, RMS output voltage. Simply remember, most of the formulas are similar to R load. With freewheeling diode, similar to R load, except conduction angles. Then output power. Here output power is V naught into I naught. I told one point you have to remember here. Wherever the continuous mode is there, you have to take the average power concept, not the RMS power concept. If it is a discontinuous mode, then only it is a RMS power concept. That is V naught RMS into I naught R. RMS power in the sense, you have to use RMS value of currents and RMS value of voltage. If it is a continuous mode, you have to use the average voltage. And this is the average value of diode current, RMS value of diode current. Average value of freewheeling diode current, RMS value of freewheeling diode. This average diode current equal to average source current. RMS diode current equal to RMS source current. This is input power. Source current is pulsating. This is about with freewheeling. Then what are the advantages of freewheeling diodes? Based on this also, questions are important. Eliminate the negative spikes and improves the average output voltage. If average output voltage is improved, then output power is increases, efficiency is increases, input power. That is, using freewheeling diode, negative spikes are eliminated. When the negative spikes are eliminated, average output voltage is improved. If average output voltage is improved, output power increases, efficiency increases, input power factor also increases, load current waveform becomes more continuous. All these are the advantages. But you know that freewheeling diode can work only for inductive loads. It cannot work for resistive loads. For example, this is one diode. Let us assume that this is the freewheeling diode. This diode is connected across the resistive load. But the conduction angle of this diode, it is asked. The diode never conduct. Diode never conduct. Why? Because there is no any reactive loads to drive that, to conduct that diode. That's why it works only for reactive loads. It cannot work for resistive load. Freewheeling diode cannot work for resistive load. Then this diode is also called freewheeling diode. It is also called feedback diode. Sorry. What do you mean by freewheeling diode? The diode which carry the current within the load only. What is the feedback diode? Feedback diode is different. Freewheeling diode is different. Here two diodes are there now. This diode is the feedback diode. This diode is the freewheeling diode. The diode which carry the current within the load only. The diode which carry the current to the load through source. That is called feedback diode. But freewheeling diode is also called flywheel diode or commutating diode. It's also called flywheel diode. That you have to consider. Then always conduction angle with freewheeling diode greater than as compared to without freewheeling. Average output voltage with freewheeling diode greater than without freewheeling diode, because with freewheeling diode negative spikes are eliminated. This one question you have to practice. You don't have the time to practice the formulas. Better to practice this question. Better to practice whatever the problems that I solved. That you have to consider. This is the problem with respect to RL and freewheeling. Next, RE loads. This is important. In RE load case, what is the minimum angle at which, but you don't expect any waveforms, leave it, no need to practice. These analysis points are very important. All these are single phase half wave diode rectifier. All these are the single phase half wave diode rectifier. In single phase half wave diode rectifier using RE load, every formula is important. For the peak inverse voltage, for the circuit turn off time, for the diode conduction angle in RE load, what is the minimum angle at which diode start the conduction? What is the minimum angle at which diode start? That is theta 1 equals sin inverse E by Vm. Then what is the average current expression? What is the average voltage expression? What is the power delivered to the battery? That you have to concentrate. Then what is the output power expression? E into I naught plus I naught RMS square into R. This is RMS output current expression. This is input power factor formula. Then how to calculate the battery charging time? The battery charging time equal to battery capacity by to battery. That is, sometimes battery capacity given in watt hour rating, then watt hour by power gives the time, charging time. Sometimes they given the AH rating, ampere hour by current, divided by current, then you can get the time. That is, battery rating they will give in watt hour rating or ampere hour rating. Based on that, you have to calculate the times. This question you have to practice. What is the minimum angle at which diode start the conduction? What is the peak inverse voltage? What is the circuit turn off time? What is the average current? This is the one model of question. This model is important for 2 marks. Calculating the RMS current, mainly for gate point of view, this is important for 2 marks model. Then this also you have to practice. This question also you have to practice. You don't have the time to practice the formulas, better to practice them. Next, single phase half wave diode rectifier using RLE loads. Using RLE load. Here also important points are you have to concentrate only analysis points. Then what is the peak inverse voltage? What is the circuit turn off time? The diode conduction angles theta 1 to beta. Then minimum angle at which diode start the conduction is theta 1. Then average load current expression. Average output voltage. You don't expect any questions on RMS current. Then power delivered to battery. Then input power factor, direct formula also you can expect. Battery charging. Also concentrate on the circuit turn off time. Very important is minimum starting formulas up to average current. This is important. Minimum you have to concentrate on up to average load current formulas. That is very important. Then you practice this problem. This is the question based on with respect to single phase half wave diode rectifier with RLE load. Then one more circuit is RLE load and freewheeling diode. This is 5-star circuit for our exam point. Simple questions we can expect. In RLE and freewheeling diode, the formulas are similar to RL and freewheeling diode. The analysis and waveforms are similar to RL and freewheeling diode, but only this current expression will change. In RL and freewheeling diode, I naught equal to V naught by R square. But in RLE and freewheeling diode, I naught equal to V naught minus E by R. V naught minus E. Okay, these formulas, all the formulas that I written, please go through this. For circuit turn off time, each diode conduction angle, freewheeling diode conduction angles. For the average output voltage Vm by pi. With the freewheeling diode similar to that of R load formula. What is the average load current formula? RMS output voltage formula. What is the RMS output current, output power expression? Average diode current, RMS diode current, average freewheeling diode current, RMS freewheeling diode current, input power factor, and source current here also waiting. Then practice this problem. Finally, you have to practice the questions. Try to practice the questions whatever I given. Gunshot we can expect that models only. Even the values may be different in the exam. If the questions they are asking from single phase half wave diode rectifiers, only these models only we can expect. Then this is the special circuit half wave diode rectifier with C load. With the C load, these points mainly how to concentrate. This is the C load instantaneous output current. I naught equal to Vm into omega C into cos omega t. We need to concentrate on the waveforms. This is the voltage across the capacitor waveform. This is the load current waveform. This is voltage across the diode waveform. And this peak inverse voltage 2 Vm. That's important. For purely capacitive load, peak inverse voltage is 2 Vm. This is instantaneous current expression. Diode conduction angle is 90 degrees. Purely resistive load 180 degrees. Purely inductive load 360 degrees. Purely capacitive load 90 degrees. Then for omega t greater than or equal to pi by 2, V naught equal to Vm. This voltage across the diode. Average voltage across the diode. RMS fundamental voltage. Total RMS voltage. This is for purely capacitive. This is some special circuits. If a resistor with the capacitor arrangement is there, how we can get the output waveform. If the diode is this direction, then only negative half cycle output we can get. Half cycle output. These are the drawbacks of half wave diode rectifier. Now half wave diode rectifier, only one half cycle only we are getting output. Only one half cycle we are getting output. Source current is fluctuating DC. Because of this, harmonics will increases. And these are all these are the average and RMS values are less. High ripple factor, less transform utilization factor. All these are the drawbacks. To overcome the drawbacks, then we are going for full variety. Then with respect to C load, you have to practice these questions. If any question is asked for the C load, this model of question is important. For the peak inverse voltage, for the maximum current, for the average diode voltage, for the RMS diode, fundamental RMS diode voltage, for the total RMS diode voltage, what conduction angle. Then one more important concept with respect to diode rectifiers, that is the single phase full wave. Single phase full wave diode rectifiers, again midpoint type rectifiers and bridge rectifier. Midpoint type is also called center taproot transformer. But one point you have to remember, students. Midpoint type rectifier and bridge rectifier, no need to remember the formula separately. For both midpoint and bridge, all the formulas, waveforms are same except one formula, transform utilization factor and peak inverse voltage and number of devices. These three is different. Number of diodes are different. Transform utilization factor is different. Peak inverse voltage is different. Most of the remaining formulas are same. In full wave rectifier, discontinuous mode is only in R and RE load. Remaining loads it is a continuous mode. If there is an inductor, it is a continuous mode. But in a half wave rectifier, all are discontinuous mode except one case, that is freewheeling diode case. But full wave rectifier, most of the cases it is a continuous mode except R and RE. That is, but midpoint type rectifier and bridge rectifier, same formulas, same waveforms except peak inverse voltage, number of devices and transform utilization factor. This is the configuration of single phase midpoint type diode rectifier using R load. This is the center taproot transformer type. Then these are the waveforms. How many pulses per cycle we are getting? 2 pulses per cycle I am getting. That's why it is called 2 pulse converter, whose ripple frequency is the 2f. Ripple frequency 2f. Then what is the source current waveform we are getting? For R load, source current waveform is sinusoidal. Source current waveform is sinusoidal. This is the output voltage waveform. This is the source current wave. Then finally, analysis is important. Peak inverse voltage is 2 Vm. Very important. In a midpoint type rectifier, what is the peak inverse voltage? 2 Vm. What is the circuit turn off time? R load always pi by omega. Average output voltage is 2 Vm by pi. But in half wave rectifier, Vm by pi, it is a 2 Vm by pi. Average output current V naught by. RMS output voltage Vm by root 2. This is the RMS output current. Input power factor is unity, very important. In a single phase full wave diode rectifier, not half wave diode rectifier, full wave diode rectifier using R load only. Using R load, always input power factor is unity. Important, sir. Till now not asked, but you can expect. Then what the average source current is sine wave, average source current is 0, RMS source current is Im by root 2. Then input power factor always unity. In the case of resistive load, full wave rectifier resistive. Then what are the drawbacks of midpoint type rectifier? Peak inverse voltage is 2 Vm, which increase the rating of the diode and cost of the diode. Because of center tap transformer, it requires more number of turns at the secondary, which increases the cost also. With respect to each diode, it is asked. This is average diode current and RMS diode. With respect to each diode. This problem also you have to practice. Important. This model already framed in gate exam. For the peak inverse voltage 2 Vm. Here given is, if it is given like this, these are the RMS values, students, not a peak values. No. RMS values. Then I am writing Vm in terms of RMS value root 2 Vs. Always you take the secondary voltage 50 volts, then 100 root 2 volts is the. Don't take 230. But don't take 50 directly. This is RMS value. But you have to substitute maximum value root 2 Vs. You take. That observation is. Then single phase diode bridge rectifier using R. Diode rectifier, that is midpoint type diode rectifier, that is a full wave. This is also full wave. That is midpoint type 2 diodes, but here bridge type 4 diodes are there. So this is the standard notation for diode 1342. But the formulas are same. Same waveforms, no change. Midpoint type rectifier and bridge rectifier, same waveform. But in midpoint type rectifier, at a time one diode is conducting, but here 2 diodes are conducting. This is also 2 pulse converter, ripple frequency is 2. But only difference is peak inverse voltage is V. That is for single phase midpoint and bridge rectifier, the analysis and waveform is same, except number of diodes, peak inverse voltage and transformer. This is only different. These 3 only different, remaining all are same. Same formulas you have to practice, circuit turn off time, each diode conduction angle, average output voltage, average output current, RMS output voltage, output power. This is important. Based on this formula, already gate question is there. P naught equal to V naught RMS square by R. Source current is sine wave, average source current, input power factor. But here input power factor is not equal to 1. It's a resistive load. No? Resistive load always input power factor not equal. Equal to 1 only. It may be only inductive loads only not equal to 1. Even though it is a bridge rectifier. I told already. Midpoint type rectifier and bridge rectifier, both resistive loads. If it is a resistive load, power factor is unity. Only inductive loads only not unity. Okay. Average diode current, RMS diode current. If any one diode is damaged, it acts as a half wave rectifier. Correct or not? Full wave rectifier, one diode is damaged, one half cycle only you can get output. Another half cycle you don't get output. That's why it is a half wave rectifier. And this question you have to practice. This formula is important. Based on this formula, gate question is repeated. What is the output power? Not equal to V naught R. Okay. And remaining questions also that I solved. All the possible questions I solved, students. Please practice these models of questions with respect to diode rectifier. Single phase full wave diode rectifier using R load. Next, single phase diode bridge rectifier using RL load. In RL load, it is a continuous mode of operation. In a continuous mode of operation, then source current is the square wave. Previously, R load source current is sine wave, but here source current is square wave. Source current is square. Let assume that we are supplying the constant current to the load. The constant current is supplied because the continuous mode. And peak inverse voltage Vm, circuit turn off time. Each diode conduction angle is 180 degrees. There is no change in average voltage. There is no change in average voltage. The average voltage is same. Here there is no change in the average voltage. It may be R load or RL load, same average voltage. Because the waveforms are same waveforms we are getting. Only conduction, that is the average current, RMS current will change. Because continuous current. RMS voltage also same. But RMS current is I naught here. But in R load, V naught RMS by R. The output power expression mainly concentrate, minimum try to concentrate average value, RMS voltage, output power, input power. Then source current is square wave. This is important for purely, that is for inductive loads, not purely inductive loads. For inductive loads, a source current is square wave. Average source current is 0. RMS source current equal to average load current. That is in a diode bridge rectifier or full wave rectifier using RL load. Full wave rectifier using RL load. RMS source current equal to RMS load current equal to average load current. All are equal. Input power factor is V0 by Vs, not unity here. Not unity because inductive load. This is the average diode current I0 by 2. RMS diode current I0 by root 2. Is equal to I0 equal to I. Then one more is single phase diode rectifier using RE load. In RE load, that mainly you have to concentrate on peak inverse voltage. It is not Vm plus E. If it is a midpoint type rectifier, then only Vm plus E. But in bridge rectifier, even though load consists of battery, it's a Vm only. The circuit turn off time is pi plus 2 theta 1 by 1. So this is the average load current expression. This average voltage expression, RMS current expression. Then this you have to minimum try to remember this. Not RMS current, average current and average output voltage and circuit turn off time, and you have to concentrate peak inverse voltage at what angle the diode start the conduction theta, that you have to consider. Then in midpoint type rectifier, I am not giving detailed analysis. RL load and RE load, peak inverse voltage to remaining analysis and waveforms is similar to bridge rectifier. Midpoint type rectifier given, bridge rectifier is given, same formulas. How to practice this question? Very, very important 5-star model. Here I given bridge diode rectifier. And midpoint type rectifier is also given, same formulas except peak inverse. What the average output voltage? What the average output current? What the average diode current? RMS diode current? RMS output current? RMS source? Supply power factor? Output power? All this. Any question we can expect in GATE exam. Then what are the different performance parameters of diode rectifier? This final conclusion points with respect to each rectifier, some important formulas also. This average output voltage for half wave, midpoint and bridge. This is RMS voltage for half wave, midpoint and bridge. Form factor is 1.57, 1.11, 1.1. Ripple voltage is 0.386, 3077, 3077 ripple voltage. Ripple factor. This is highest ripple factor. Half wave rectifier is high ripple factor. It is 121%. But this is 48.2%. Rectification efficiency. This is 40.53, but it is 81. That is 81.068. But this is different that you have. The transform utilization factor of midpoint is 67.2%, but it is only 81. But it is 81. That is less transformer utilization factor. Remaining all the parameters are equal. One parameter is different, but no doubt at all. Half wave rectifier is very less. But in this, again, center tapped is less transformer utilization. And peak inverse, this also different. Midpoint type rectifier 2 Vm, but here it is a Vm. But half wave is also Vm. That's crest factor 2, it is a root 2. How many number of diodes? Here 2, but here 4 diodes. Ripple frequency no change, it is a 2f. Ripple frequency. That is, the output voltage of full wave rectifier is 2 times of output voltage of half wave rectifier. RMS output voltage of full wave rectifier is root 2 times of RMS voltage of half wave rectifier. Peak inverse voltage of midpoint rectifier is 2 times of bridge rectifier. Then RMS output voltage of full wave rectifier Vm by root 2. RMS voltage of half wave rectifier is Vm by 2 square. Then number of diodes in bridge rectifier equal 2 into number of diodes in midpoint. Transform utilization factor of bridge rectifier is greater than next midpoint, next half wave. Ripple factor of bridge and midpoint is same, but ripple factor is more in half wave rectifier. Efficiency is more in bridge rectifier and midpoint is also same, but efficiency of half wave rectifier is, that is, both full wave diode rectifiers are better than half wave rectifier as voltage ripple factor, rectification efficiency, transform utilization factor and crest factors are considered. Both are better as compared to half wave. Both full wave rectifiers have average output voltage double that of the half wave rectifier. Full wave rectifier have ripple frequency double than that of the half wave rectifier. That is, full wave rectifiers are better perform. Transform utilization of bridge rectifier is superior than midpoint type rectifier. Therefore, transformer required in midpoint configuration bulk and weighting. Peak inverse voltage of bridge rectifier is half of that of the diode midpoint type. Vm, but midpoint 2 Vm. Bridge rectifier requires 4 diodes, whereas midpoint type requires. Overall, which is the more preferable bridge rectifier using 4 diodes is the more economical configuration. Which configuration is the more economical configuration? Bridge rectifier using the 4 diodes is the more economical. This is the special case. Still now not framed, but you can expect you remember this. Maximum they will ask the current waveform. A bridge diode bridge rectifier is not a thyristor. It is a diode bridge rectifier with purely inductive load. The current will continuously increase. That's why this process will be continued, either load will be damaged or source will be damaged. That's why it is unstable operation. Diode bridge rectifier with purely inductive load, current is continuously increases. That's why it is unstable operation. That point. Next, in rectifiers, if you consider the leakage current effect, that is reverse recovery time due to leakage current. In the diode explanation that I given, what is the reverse recovery? Due to leakage current, we are getting reverse recovery. Due to reverse recovery time, leakage current, we can get the negative spike. If you don't consider reverse recovery time, we already seen the waveform. By considering the reverse recovery time or leakage current effect on the diodes, these are the waveforms. Then because of these negative spikes, average output voltage is. That is, due to leakage current or reverse recovery time, conduction time of diode is increases by TRR and total conduction time is pi by omega plus T. Important. What the total conduction time? These are the special cases. Still now not framed, but this was expected. This circuit is also expected. This circuit is also expected, friends. Still now not framed. This circuit in the sense, this concept is also. Average output voltage is reduced. Due to reverse recovery time, average output voltage is reduced. How much average voltage is reduced due to TRR time? This is the formula. This you have to substitute in degrees. So you multiply with 180 during solving of the problem. Then this is the special observation that you have to remember. Generally, both midpoint and bridge rectifier is same output voltage. But if they given voltage across the diodes, in midpoint type rectifier only VD is subtracted. But here how much voltage is subtracted? 2 VD is subtracted. Why? Here at a time only one diode is conducting. Here 2 diodes are conducting. More voltage drop now. That is 2 VD is subtracted. That's why which rectifier is more output voltage? Midpoint is more output voltage as compared to bridge. If they given the voltage across the diodes. If that statement are not given, both are same average output. And this model also you have to concentrate. Sometimes they are asking what is the secondary VA rating of transformer. Secondary VA rating means VSIS. Then VSIS equal to PDC by TUF. But you already know full wave rectifier, what the transformer utilization. Sometimes they don't give transformer utilization factor. Already you know the transformer utilization factor. That you divide with 0.81. This gives the VA rating of transformer. Sometimes, still now not framed, but you can expect. If they ask the VA rating of transformer, you try to remember the transformer utilization factor of different types of rectifier. Yes, friends. This is about some introduction to power electronic circuits. Some important fundamental observations from power electronic circuits point of view. What are the input performance parameters? What are the output performance parameters? How to solve the problems? And with respect to rectifiers, in detail that I discussed about single phase diode rectifier. In single phase diode rectifiers, single phase half wave diode rectifiers, single phase full wave diode rectifiers. In full wave again, midpoint diode rectifiers and bridge rectifiers. Also I explained. In that I given so many important formulas and important problems also that I given. Please go through. This is about the session.